Today we're looking at graphing these polar equations that we were kind of working with algebraically yesterday. Now, how do they work on our polar graph? There are a couple of features that you're looking at when you're graphing. One of those things is the maximum R value. The R value, remember, is how many rings out it goes. The maximum R value means wherever you're at on the graph, where's the farthest out that it gets? We call that the max R value. And it's going to occur when a point on the curve is at its maximum distance from the pole, okay? Now here's what's tricky though. R can be positive, but remember it also can shoot backwards through the polar graph, so it might be negative. But you're still looking at how far from the pole is it, so we will always use the absolute value of R as the max R value. We still look at domain and range, but what's different is the domain is really your theta, and the range is the R value. We look at symmetry, but it's not x-axis and y-axis symmetry. It's now called polar axis symmetry. Remember, the polar axis is the positive x-axis, so this is like, we don't call it x-axis symmetry, we call it polar axis, but it's kind of like x-axis symmetry. And then we have this pi over 2 line symmetry. And the pi over 2 line is like your y-axis, but it's not called the y-axis. So when you're looking, though, at the graph, you're thinking it looks like y-axis symmetry. And then you have pole symmetry, which means it's around the actual pole, and that's kind of like origin symmetry. Just trying to tie this back to what you're familiar with on your rectangular graph. Here we have a nice fancy polar equation. Remember, it always starts off with an R equals something with a theta in it. And just like in Algebra 1, when you first started to learn how to graph a line, we started by making a table. And when you first start on a parabola, you make a table. That's how we're starting here today. Let's make a table and let's plot some points and see what happens. Get those calculators out, because if we're going to plot these, we kind of need these to be in decimal form. Maybe I'll come back and do the decimals after a bit. Let's start off, and because I want this to be kind of quick, I'm going to go ahead and just use values that I know from the unit circle. If you don't know your unit circle, this is going to be a little trickier. If you know your unit circle, things are going to be good. I'm going to do this mentally because I know my unit circle. We start off and we're going to plug in numbers for theta. Theta, remember, is our domain. So plug in whatever we want, but I'm going to pick values I know. And I put in 0 right here. And I just kind of do order of operations. First thing I'm going to do is say the cosine of 0 is, always think unit circle, cosine of 0. Maybe what I'm going to do, hang on, just so that you can visualize. Cosine of 0 is 1. But that 1 is going to be multiplied by 2, which is just still 2. In the end, I do 1 minus 2. Well, that was easy. That's just negative 1. Let's try the next one. Pi over 6 is up here. My cosine is root 3 over 2. If I have 2 times, and sometimes I'll show this here, but we're going to start doing it in our head. 2 times the root 3 over 2. 2's are going to cancel. I just get root 3. And then 1 minus the root 3. That's where I'm going to go to my calculator. 1 minus the square root of 3. That's a negative 0.7. I'm not going to get very many decimal places because I'm going to be estimating these on my graph anyway. I'm going to be happy with my 1 decimal place. So I'm going to go negative 0.7. Let's do pi over 4. That's right here. The cosine of pi over 4. That's a root 2 over 2 times 2 is just going to be a root 2. 1 minus root 2. I have negative 0.4. All right, let's try pi over 3. Pi over 3 is up here. The cosine is 1/2. 1/2 times 2 is just going to be 1. 1 minus 1 is 0. That works out nice. Let's keep going. Pi over 2. The cosine is 0. So cosine of pi over 2 is 0, times 2 is 0, and 1 minus 0 is 1. 2 pi over 3. That's up here. The cosine is going to be a negative 1/2. Oh, okay, so now this number that I'm multiplying by, I know I have a root 3 there, but I know it's now a negative 1/2. Which means that when my 2's and I multiply by 2, it's going to cancel out. It's going to be a negative 1. Now be careful with that because it's like, I'm still subtracting, so it's 1 minus negative 1. That's 1 plus 1. That's a 2. Okay, let's try again. 3 pi over 4, that's over here. So that's a negative root 2 over 2 times the 2. The 2's cancel. I get a negative root 2. But it's going to be 1 minus negative root 2. That's 1 plus root 2. How you doing on your mental math? It's good number sense. Good to force yourself to practice doing that. Don't trust me. I might goof up. All right, next one. 5 pi over 6. That's this angle. My cosine is negative root 3 over 2. Times the 2, that cancels, I'm left with a negative root 3. 1 minus negative root 3 is really 1 plus root 3. I have 2.7. Let's try one more, and then I'm going to start plotting and seeing what happens. Let's plug in pi. Over here at pi, the cosine value is negative 1. Okay, that's negative 1. 2 times negative 1 is negative 2. 1 minus negative 2 is really 1 plus 2. And I'm at 3. Okay, that's a lot of different numbers. Let's see what that looks like on our graph. When I graph, I know that it's really an ordered pair, r comma theta. But in my head, I always get to the right angle, and then I go out that many rings. These are how many rings I'm going to go out. This is what my angle is. So at angle 0, I'm going to go out negative 1 rings. Remember what that means? It means you're back, instead of coming out this way 1, you're going to go back that way 1. There's my first point. At pi over 6, remember that we don't really use this one. This is the first one we know from unit circle. At pi over 6, instead of going out 1, well, actually I'm not even out 1, I'm out 0.7, but since it's negative, I got to go backwards through that. Not quite to the first ring yet. Let's see if I can make this plot like I want it to. Probably not. I'm going to have a hard time getting that precise. Okay, I'm going to go with that. Not very pretty, sorry. Let's go to the next ordered pair. At pi over 4, that's this middle mark right here, I'm at negative 0.4. Well, gosh, that's even closer to the pole, but still going backwards. So now I'm somewhere in here. Put a dot. I'm not quite at the pole, but I'm kind of close to it. Oh, the next one, I'm at pi over 3, and my radius is 0, so I am truly right here at the pole. Okay, that's kind of a mess of little points. Now, I hope you're plotting nice, neat points on yours. The next ordered pair is at pi over 2, and I'm 1 ring out. Pi over 2 is straight up 1 ring out. 2 pi over 3, I'm 2 rings out. Now we're starting to jump bigger. And at 3 pi over 4, I'm between the 2 and the 3. And at 5 pi over 6, I'm closer to the 3. And then at pi, I'm at the third one, right there. Okay, do you see kind of how that looks? It's kind of a little spirally thing, isn't it? Okay, it's actually not, though. It's not going to be a spiral. And we don't know that until, but this is the first time we've done it, and just doing that much maybe isn't enough. I got us started on our table, but I don't think that that's enough to confirm it's just going to spiral out, 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 out. Let's go ahead and keep going with a table. I'm going to come down here where I have some more space. Since this is the first time, I really don't know what this thing is supposed to look like. But I'm going to keep going with my thetas that I know off of my unit circle. So the next one is a 7 pi over 6. And then after that is a 5 pi over 4. And after that is 4 pi over 3. And 3 pi over 2. 5 pi over 3. 7 pi over 4. 11 pi over 6. And then we land at 2 pi. So we're going to go around that many more times. So this is some more mental math for us. Here we go. At 7 pi over 6, thinking around here, 7 pi over 6, the cosine is negative root 3 over 2 times the 2. So here's my negative root 3 over 2 times the 2. They cancel. I'm at negative root 3. 1 minus negative root 3, 2.7. Five pi over 4 is down here. My cosine is negative root 2 over 2 times the 2, negative root 2, and then 1 minus a negative root 2 is 1 plus root 2, which I think I did earlier. Didn't I do that earlier? 1 plus root 2? That was the 2.4. That should make sense here, because aren't I going to be using the cosine values that I have up in this quadrant are the same as the cosine values I have in this quadrant. They're a negative something or the other. If I'm getting the same values, then when I plug it in here, if I get the same value for this cosine, the rest is going to be the same. Could you guess what the 4 pi over 3 is going to get me? Four pi over 3 is here. Cosine is negative 1/2. Negative 1/2 times the 2 is a negative 1. 1 minus negative 1 is 2. Did you have that? And isn't that going to keep happening? If I'm down here at 3 pi over 2, my cosine is 0 times 2 is 0, and 1 minus 0 is 1. I'm just backing my way through this. Can I just finish it then? The next one's going to be 0, because now I'm over to this quadrant, and these cosine values will be the same as these cosine values, which are all the ones I just finished this way. That's that symmetry happening. And then negative 1. And I want to check that last one just to be sure. At 2 pi. At 2 pi, the cosine is 1 times 2 is 2, and 1 minus 2 is negative 1. It checks. All right, let's plot these things now. At 7 pi over 6, I am 2.7. Oh, see how that matches the point right here that we had? And then I have a 2.4 on my next one, which is about here-ish. So you can see this is not spiraling out. This is actually coming back in, isn't it? At my next one, at 4 pi over 3, I'm at the 2 mark. And straight down, I'm at the 1 mark. Radius of 1. And at 5 pi over 3, I'm back to the pole. And then, as I wrap around and I'm over here in this fourth quadrant, when I'm plotting these, I have negative values. So those are going to actually go through up into this quadrant. Now, you're going to have to be graphing these nice and neat on yours, because you know my graphics aren't awesome. At 5 pi over 3, I already did that one. Okay, at negative 7 pi over 4, that's the middle one, the 45, I'm at negative 0.4. So that's in here someplace. And then at the 11 pi over 6, I'm a little bit closer out there. And then at 2 pi, this is kind of the important one. At 2 pi, I'm at -1, which is actually right back where I started. That was my very first point. Now, hopefully you can see it a little bit better, but even probably on your graph, it's not perfect. We had to kind of plot this. We had to do it the long way to get the gist of it, but it's important to do that so you know the order. You have to plot these. You have to connect this point to this point, to this point, to this point, to this point, to this point. You have to wrap around this thing in the order that we plotted those. Here's what this graph actually kind of looks like then. It has kind of like this loop thing going on right here. And then it kind of goes around, or it's kind of like a spiral thing. But then it comes back inward, 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 and comes around and loops back to where it started. And there's like this little loop inside of this circle thing. Okay, that is crazy. That is not something that we have ever seen before on a rectangular coordinate system. We can graph it on our calculator, but you have to do a couple things. I can't do that on the video, but you can try it. You have to go to, you have to change some things on your calculator to graph this. First thing you want to do is go to your mode. And you should be in function mode. It's underneath the radian degree option. You have to switch that over to polar mode. The other thing that you're going to have to do is change your format. That is a second zoom. On second zoom, you want to change that from rectangular graphing coordinates to polar graphing coordinates. And that should be sufficient. And now, you'll notice that if you go into y equals, it's no longer a y equals. By switching the mode, it's now an r equals. So you can type in 1 minus 2 cosine. And now when you push your x button, it actually shows a theta. That's what that means, that x, t, theta, n that you have on that button. Those are different options depending on the mode that you're in. Before you try to graph that, you probably need to fix your window. And your window, if you think of what this would look like on the coordinate system, you're kind of going from -5 to 5. But the very first thing in your window talks about your theta and what you're doing for your thetas. And this will tie in what we're going to do right here. I hope you're doing this in your calculator with me so you see what I'm talking about on your screen. If not, pause, get your calculator out and do those things and get with me. The domain on the previous screen, I told you that the domain is the possible theta values. Well, these are my theta values. Now, these happen to be the ones I chose off the unit circle. I didn't have to pick those. I could pick anything I want. And I could go forever. I could back this up to negative angles. It's still going to get me anything that I want. So my domain is going to be -infinity to infinity. The range comes from this table of R values. This is another important reason why we had to do the table to see. It's really tricky to look at this and see what your range is. It's not your Y values, it's your R values. And if you were to look at this, it'd be a little bit tricky. If I were to guess my R values, it's basically what the smallest R is and what the largest R is. It looks like the smallest R value I ever have is this -1 right here. It's actually the inner part of that loop is where that point was. It was that very first point. But it's kind of weird to think of that as your range. So the smallest R I ever had was -1. What's the biggest R? It's a +3. When you look at your table, you see it right here. But if you were to look at this graph, I bet you'd think of that as a -3, wouldn't you? All right, that's weird. If you go to your window, I'm going back to my window on my calculator, you can see these, you have to decide on your window, first of all, your theta values, your theta min. Well, my theta min happened to be 0. My theta max was 2 pi. So actually mine already says 6.28 is 2 pi. You can type in 2 pi if you want. The theta step is, what do you want to increment by? Now, my calculator doesn't have to match this exactly, because remember, I could have put anything in there. Typically, what we want to do a theta step by is not, I mean, just like here, you had to kind of know what this was going to look like to be able to graph it. We probably need smaller increments. I'm going to put in, and what is very typical is to put in pi over 16 and plot every pi over 16. That's a lot more points than I would have had. All right, so I put in pi over 16 for my theta step. And then I still have to do x and y, which is kind of like your axes or your r's. I'm going to go -5 to 5, scale it by 1, do the same on my y's, scale by 1, and finally I can graph it. And you should see this thing graph in the order that we plotted it. It should, and depending on how fast your calculator works. All right, I goofed up. Remember when we put theta over 16? I'm sorry, pi over 16. That also means I need to be in radian mode. Go change your mode, not just to polar mode, but change it back to radian, because I was in degree, so I need it to be in radian. And now I'm going to hit graph. I was going to say I couldn't see it. It wasn't coming up. All right, and it plots this nice little loopy thing. If you want to trace it, and you hit your trace button, it starts off with this very first point right here. And then if you move to the right, it'll start wrapping around and it'll plot just in that exact same order that we did when we were graphing it. What I want you to notice as you do that, that's how you're going to find your max R value. That's how you know if this is a +3 or if that's a -3. You can't tell just by looking at the graph. Unless you have a table, you're going to have to trace this on your calculator to know what's the smallest, what's the largest. And you just sit there and track it to see. So keep that in mind. Don't trust the graph when you're doing that. All right, now that we have talked about the range, the symmetry, you can just glance at it. Oh, it looks like it's x-axis symmetry. We don't call it x-axis symmetry. We call it polar axis symmetry. And your max R value is always going to be from your range, whatever the maximum range value. The max R value, the farthest it ever gets away, is 3 units. Okay, now that was a marathon slide, I know, but it was your very first one. We're going to get better. Let's try one more. This is a different type of equation. There's no addition subtraction, so this should be a little bit easier for us. It's just 4 cosine 3 theta. Now what this is it's not the 3 in front. It's not 3 times the cosine of theta. You're actually taking your angle times 3. And then you're taking the cosine of it. Again, I'm starting off with this basic table, and we'll see where that takes us. I'll throw up this graph here if that would help us with knowing those angles and our unit circle stuff. Let's start with 0 degrees. Okay, so the first thing you're going to do is take it times 3. Well, 3 times 0 is still 0. The cosine of 0 is 1, times 4 is 4. Pi over 6. The first thing I'm going to do is take my pi over 6 times 3. Well, that's 3 pi over 6, which is really pi over 2. So that really jumps me to this spot. Not that that's where I would plot it. I would still plot it at pi over 6, but thinking unit circle, the cosine up here at pi over 2 is actually 0. Times 4 is 0. Pi over 4. Times the 3 is 3 pi over 4. So in my head, I'm really over here because that cosine value is -√2 over 2. And I have to take that times 4. So think of that times 4 over 1. All right. So the 4 and the 2 can reduce, so this is really going to be a 2 times -√2. So I'm back to my calculator to get some decimals. This is -2 times √2 is what that boils down to. And I get -2.8. Okay, pi over 3. Here's pi over 3. But I have to take it times 3. Well, that's easier. That's pi. So the cosine of pi is -1 times 4. -4. All right, I'm at pi over 2. Got to take my angle times 3, so that's 3 pi over 2. Again, that's an easy angle. 3 pi over 2 is down here. What's the cosine? 0 times 4, 0. See how this is going a lot faster for us? 2 pi over 3. Okay, 2 pi over 3 is right here. But the very first thing I'm going to do is multiply to, okay, now remember, again, when I say 2 pi over 3, I'm really going to be plotting it down here on this graph at 2 pi over 3. But to figure out my r value, I have to take that 2 pi over 3 times 3. Well, that's 2 pi. So in my head then, when I'm evaluating, I'm over here. And that cosine value is 1 times 4. 4. 3 pi over 4. Okay, but the very first thing I'm going to do is take 3 pi over 4 times 3. That's 9 pi over 4. 9 pi over 4. Well, gosh, what would that be? Where would you be? Well, right here is 2 pi, or 8 pi over 4. So 9 pi over 4 is just one more. So it's like a 45. It's that same one. Okay, so cosine there is root 2 over 2, but it would be positive in that quadrant, times the 4, that would reduce to just a 2 root 2. That's the same number I had earlier, just now it's going to be positive, 2.8. 5 pi over 6 times the 3, that's 15 pi over 6. I could reduce that though. 15/6 is really 5 halves. All right, so 5 halves. Here's 1 half, 2 halves, 3 halves, 4 halves, 5 halves. Okay, so I'm really just straight up. And that cosine value is 0. Times 4 is still 0. Last one, pi. But I'm going to take it times 3. That's 3 pi. Well, that conveniently lands right back where I was. So 3 pi is right here. That cosine value is -1. Times 4 is -4. All right, so let's go plot this and see how this plays out and see if we have to extend our table. At 0 degrees, I am 4 units out. 4. Okay, at pi over 6, I'm 0 units out. At pi over 4, which is this ring, but I'm at -2.8, so almost to the third ring there. All right, then at pi over 3, that's this angle, but I have to go a -4. Pi over 2 is just back at 0. I already have that point plotted. 2 pi over 3, that's this one here. And it is at a +4, so that one stays right here, 4. And then at 3 pi over 4, I'm at 2.8. And then back to 0. And then at pi, I'm at, and this is pi, I'm at -4, and you know what? I've already plotted that point. And what's going to happen is it's going to actually start repeating from there. Now, whether or not you would have known that, maybe not, I'm just helping you out because these points also aren't probably going to tell you what this looks like. We would have to make much, much smaller increments to be able to really see what this is doing. But we need to kind of see this table so we can answer our questions and know the order in which to graph this thing. If I were just to start off and look at my table and do my domain and range, the domain is the possible theta values. Well, there's nothing particular about that. I could have put in any angles I wanted. It still goes -infinity to infinity, and typically will. All right, your range is your possible r values. Let's look at what we got for some r values. What is the smallest r value you see? Looks like it's a -4. And the largest, +4. Did I use brackets on that last one? I should have. I don't think I did. Okay, the symmetry on this one. Well, I think I might need to sketch this whole thing before I could pick out my symmetry. But my max R value is the farthest, or the farthest out from the pole that I ever get, which happens there and there and there, and I'm 4 units out. The max R value is 4. Let's go over here and graph this thing. I started, my very first point was this one way out here. And then my next point was this one. You might think that that's a straight line shot, but if I were to have put in other values, smaller increments in here, I would have had a few other points. It's actually more of a curve. And so it goes from here to here to here to here. So it's going to kind of curve up a little bit and come back. Hit there, and again, then it shoots there, but it's actually a little curve. If I had a few more, it would have a little curve to it. And then from there, you're supposed to go to there, again, add a little curve into it, come back to this point, and you're back to there, and then back out to here with a little curve. All right, so I'm going to draw it now. Real deal. It starts out here, comes in with a little curve, comes out, add in a little curve, comes out, add a little curve. Remember doing a spirograph? Did you have a spirograph when you were little? Do you even know what a spirograph is? It's kind of like that. It's making these little spirally things. Okay, it's not really a spiral. It is actually what we call a rose curve. And we could graph it on our calculator. I'm not going to on this one. I'm trying to hurry this along. You can trace it to see where your max R value. You can look at your R's and your thetas and everything. I'm going to say when I look at this one, as far as the symmetry, it looks like another one where you could reflect it over this x-axis and it would land on top of itself. So we call that polar axis symmetry. All right, let's talk about, those are the only two that we're going to do. These are the types of graphs that don't convert nicely to what we have done with the rectangular. You know, we did like, yesterday we did like some lines and we did that circle one, but not everything converts nicely. This one right here, like I said, is what we call a rose curve. Now that doesn't really look like a rose, but depending on what you do with this equation right here, this is the typical format. You're going to have a number. This is going to be cosine or maybe sine, and then this number will change. And as you change these numbers and switch between cosine and sine, different things are going to happen. That can be way fancier. I tried to keep it simple since we were having to do this table, but this could get way fancier than that. On that previous one, I forgot to write what that was called. On this one, and again, this is any kind of an equation that looks like this, where you have a number, plus or minus, you got some coefficient, this could be cosine, this could be sine. And as you change those different features, this little graph will change. I forgot to write this. This is what we call a Limacon. It's spelled like this. I don't know if I'm pronouncing that right. It's a French word, and there's this little squiggly thing. Like I said, I never took French. I don't know what the official thing is. Limacon is how that is pronounced. And it's the thing that has the little circle with the little loopy thing in there. The other one is the rose curve. Your assignment is going to be, now we did those two by hand, and you're going to have to be able to do some by hand because you don't necessarily always know what you're dealing with. But ultimately, what we would really like to do is just like we can graph a parabola without making a table anymore, we'd like to be able to do that with rose and Limacon curves as well. But we have to figure out the patterns and what everything does. So what you're going to look at is you're going to start off, and you have a discovery worksheet, or you're supposed to, and you have a few book problems. These book problems, you're doing this one, and then this other equation, and you're doing a table, and you're graphing those out. Now, you're going to see that they take a little bit of time. You're going to hopefully get faster with it. Then we're going to do the discovery worksheet and see if there's anything that we could pick up on that might help us with some patterns that might hurry us along a little bit. Go ahead and try these first so that you get the hang of what you're doing, and then this will probably make more sense as you do it. Now, I would say at this point, if you missed day 1 of this, you can go ahead and stop and quit at this stage. You don't really need anything else from this video. If you missed the second day's worth, then you probably should have already fast forwarded through all this. Sorry. I should have mentioned that at the beginning. But you can, again, if you're, don't inundate yourself with more information. Go ahead and stop now and go work on your homework. All right, this video is now for you if you missed day 2 of the graphing. And you probably missed out on all of our classroom conversation about kind of when we did our discovery, what did we start noticing happen? So here, I'm just going to cut to the chase. I'm going to assume you've already done that, or we're just to the point where we need to just share this information. But let's talk Rose curves first of all. On Rose curves, these are the ones that had the number in front. You were sometimes doing cosine, sometimes doing sine, and you had some coefficient on your theta that you had to take your angle times. Now, this is kind of the summary of what's going to happen. Your initial point is always when theta is 0. If you think about that, if you put in the cosine of 0, that's always going to be 1. The cosine of 0 is 1. 1 times a is a. So cosine is always going to start, when you're plotting this, if you think about this, cosine is always going to start at whatever, at 0 degrees, it's going to start at that a value right there. It's going to start that far out. That's where the petal begins. But if you're doing sine of 0, if you plug 0 in for theta, or I should put it over here, the sine, regardless of what n is, if you're going to get a 0 here, the sine of 0 is always 0. And it doesn't matter what a is, you're still going to get 0. So your starting point, if you're doing sine, is always at the pole. Okay, so that, just so you know kind of where to start graphing. A, this number out here, if you would have practiced that and plugged those in, is actually always going to tell you what your maximum R value is. It tells you how big the petals are. That's the farthest ring out where the petals touch. That's important. That determines the size of the petals. Now, what you should have figured out is if n here is odd, it does something different than if it is even. If n is odd, yesterday we did that and n was 3, and we had 3 petals. If your coefficient is odd, you're going to have that many petals. So if this is a 3, there's 3 petals on a rose. If it's a 5, there's 5 petals, and so forth. However, if n happened to be even, 2, 4, 6, 8, then there were always twice that many petals. So if this is a 4, my rose actually has 8 petals. This right here should kind of tell you, so a couple other things in addition to that. That would be key stuff that you should have kind of caught on to. These 3 things definitely should have caught on to that. If you're going to try to graph this without making a table and without a graphing calculator, I think the other thing that you can kind of, that you should maybe start to notice is if it's a cosine, think of on your unit circle, the cosine problems, cosine is always your x value. This is always going to have polar axis symmetry. Whereas sine is like your y value, so it's going to have that, what we call pi/2 line symmetry. That might help you figure out where those petals go and stuff. All right, so that's kind of the quick summary to kind of help you to shortcut the process of graphing rose curves. Limacon curves are a little bit trickier. Okay, now this part is kind of important. Well, it is important, but even before we do that, we should catch on to some of the format of the equation. Remember that the equation was something like r equals, and I'll call it a, and it was a plus, but sometimes it was a minus, b, and I'll go with a cosine theta. That was that format. Now, the a and the b, depending on what those values are, will tell you the shape of this. So it's going to be a Limacon with a loop if you take A and divide it by B and you get a number smaller than 1. Okay, well that's a fancy way, that's a nice textbooky way, but for this to divide by this and be less than 1, then that just means A has to be less than B. So that might be another way to think about that. If A is less than B, then you're going to have this nice Limacon with a loop. That's what we had yesterday. If A and B happen to be equal 1, which of course just means that A and B are the same number, then what we do is we call it a cardioid. It's kind of like a heart. It has this dip. Okay, so let's go ahead and graph this one. The one we did yesterday was the Limacon with the loop, and it kind of looked something like that-ish. The cardioid does not have the loop, but it just dips in, and it would look like that kind of thing. And if you look at it sideways, it looks like a heart. So it's a cardioid. All right. As that ratio changes, and I'll jump clear down to the last one. If A over B, okay, so this is kind of the cutoff, A and B being the same thing. And now somewhere in here, A is now going to be bigger, or I'm sorry, that ratio is now bigger than 1. So it's A is now going to have to be greater than B. But this one also, A is greater than B, but there's a more drastic variation because that ratio is now even bigger than 1, it's bigger than 2. So this is kind of middle of the road. This means there's a dramatic difference between the two of those. Okay, if that's the case, A is bigger than B, slightly, or more so, what happens is this indentation gets less and less defined. And so dimpled means it's just hardly dipped in at all, kind of just like a little, I don't know, that's not even very impressive, but it has this little dimple in it. And convex, if you remember from geometry, means it's not going to dip in at all. These would be concave. So if you can get that ratio, it's not quite a circle, but it just doesn't cave in. I don't know, that doesn't look very different than a circle, but it is not a circle. That's kind of the progression as this A and B change. Now, the other thing is how this little Limacon gets oriented. I oriented it the same way that we had from yesterday, where okay, and so let's talk about a few things. And you can add these in on the side or down here, wherever you want to. If this is cosine, then it's going to have, just like with the rose curve, it's going to have polar axis symmetry, which is going to make this little loop or this dip or this dimple or whatever, it's going to make it happen on the side. It's either going to be on this side or it'll be on this side, one of the two sides. And which side would depend on if this was a plus or a minus. If this is a plus, then it's going to happen on the right side. If this is a minus, it's going to happen on the left side. Okay, so that actually isn't too hard to remember. You might pause the video and jot that down. The second part then would be, what if this is a sine value? Well, what that would mean is this loop or this little dip in here is going to be up and down because it's now going to have pi over 2 line symmetry because it's now a sine value. Think y value. So now it's up and down, and if it's going to be up if this is a plus, and it's going to be down if this is a minus. Now remember, our goal is to look for a shortcut to not have to make that big old table every time. Let's see how we did. Okay, there's one other thing that I want to talk about, and that has to do with how big do you make the Limacon. All right, well, this B value and this A value help determine that. As far as how far out from the pole it gets, the A and the B, if you add, and again, this is something you're going to want to put in the margin of the screen someplace, but if you add the A and the B, don't pay attention to this sign in the middle, but if you add these two values, that's always going to be your max R value. That's going to be the biggest chunk, or the biggest part. So whether it's a cardioid where it goes out, how far out that goes is always going to be whatever A plus B is. If you have the loop, the bigger part of it is going to be the A plus B. And that's kind of all you have to know, unless it happens to have the inner loop, because we would want to know how big the inner loop is. And that conveniently is always the difference of A and B. So add the two to get the maximum R value, subtract the two if you've got yourself a loop. And remember, it's only going to have a loop if A is smaller than B. Could we graph these without a calculator, without a table? Let's see. All right, this one. This is going to be, the first thing you should recognize is that, hey, this is going to have a, or that this is a rose curve, whereas this is a Limacon curve. On my rose curve, remember that this A value here tells me how big the petals. Or I don't know why I'm writing big petals. That doesn't, I don't know that they're big. How about petal size? Let's write that. That's the petal size. So I'm going to go 3 rings out. That's how big the petals are going to be. Now this right here, if you'll look back, it's an even number. What does that tell you about your petals? You should have double that. This is going to have 8 petals. As far as where to start graphing this, if you'll look back at your notes, we said if this is cosine, the very first point falls right here on the x-axis. The cosine petals will, or if it's a cosine equation, it's always going to have a petal right over the top of this polar axis right here. Whether it's an even or an odd, it's always going to have a petal right here. Whereas sine is not. Sine started here, which means its first petal is like in the gap somewhere here. All right, I have 8 petals, and I know that one of them is going to be right here. It's going to hit right there at that spot. All right, I've got to evenly distribute my 8 petals. Well, if there were 4 petals, they would all hit here. But I need 8 petals, so it's going to hit in the gaps also at all the 45s. And that's where my 8 petals have to be. Now, how do we draw those? Well, I don't know. Because I've done it a few times, I kind of know how this falls. But since this happens to be a 4, my first one will be here. And then my next one will be 1, 2, 3, 4. Well, I take that back. There's going to be 4 between this. So 1, 2, 3, 4. But then this is where it'll hit. And then 1, 2, 3, 4, which means this is where the next one. It'll go here to here to here to here. Okay, so that's if you were drawing it like we were graphing it the other day. That's what it would look like. It would go from there to there. And then it would come up to here. And then it would go 1, 2, 3, 4. My next one is down here. Oh my gosh, that was bad. Let me undo that. It should go through the origin every time. So make sure your petals go through the origin there. Not the origin, the pole. Now, I'm trying to draw it like it would actually graph. If you can just get the petals all in there, so their tips are in the right spot, that would be great. A lot of people just do each petal individually. That's what I'm going to go with right there. Got my 8 petals. They're located in the right spot. They're the right size. There's my rose curve. I didn't have to make a table. I didn't have to use my calculator. All right, let's look at this next one. This equation right here. This is the Limacon because of the subtraction we have going on. Okay, now let's see what we remember from the Limacon. First of all, remember that if A is smaller than B, that's the time that we're going to have the loop. This is going to be one of the Limacons with a loop. If I add these two numbers, that'd be a 7. That's going to be what my biggest loop is. And if I subtract the two numbers, it's going to be my smaller loop. So that's going to be 3. As far as which direction the loop goes, well, the sign tells me it's going to head up and down. Because it's a minus sign, my little loop is going to be downward. Here's the gist of what that's going to look like. Can't draw that very good. Sorry. That idea. That's what it's going to look like. But let's make it a little rounder looking than what I just did there. Now you can see that my graph is not actually big enough to do this one because the sum is supposed to be 7. I need to throw a couple extra tick marks out here. So I am going to move my picture up a little bit so I have a little more space. Okay, so then I'm going to have right here, if I extend this down, I'm going to call this 6, and here's 7 out here. Now, I know what the shape of this is supposed to be. I know that my big loop is going to have to come down here and hit there. My little loop is going to have to come down and hit at 1, 2, 3. I need to be going through the origin here, but when you do these limacons, I didn't do a very good job here. Look at that mess going on at the origin. You really should be hitting right there at that pole. I keep calling it the origin. It's the pole. Each one of those is supposed to go through the pole when you draw that. I shouldn't be overlapping mine. My graphics are not awesome with this app, unfortunately. Hopefully you can do better than I did. Don't let your petals overlap there. When you make this limacon, the loop is going to be down here, but your bigger loop is actually going to end up having to come up past the x-axis or the polar axis and down. Let's see if I can do this. Make this nice and round. Don't make it skinny. Makes it round. It stays kind of below, but here when you come back, it kind of goes up and past that x-axis. Oh, that's not going to be very good. Try to make that round, 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 round. And it kind of comes up past and then hits like that. And that's what that limacon is. We didn't use a table, didn't use our calculator. We're smart people. So if you can remember any of those features, any of those little shortcuts, if you can remember those, they save you a lot of time with making your graphs. On your test, the table will be there for you if you need it, but then there's going to be part of it where I'm going to expect you to recognize, oh, this has 8 petals, that kind of thing. Need to know those rules, but you can always go back to the table, I suppose, and to check it if you've got time. All right, on your homework, you can use our shortcut. If you use your notes, you should be able to work through those graphs without having to do a table or calculator. Good luck.